Welcome friends. In today's lecture we are going to discuss maximum shear stress theory. It is also known as Guest's theory or Tresca's theory. In previous lecture we have discussed maximum principal stress theory and maximum principal strain theory. If you want, you can go and study the previous lecture, those two theories. So what this maximum shear stress theory tells, it says that for no failure, that means if you want a material or machine component can sustain a particular complex load condition without failure, then the condition given by the guest is that the maximum shear stress in a complex loading condition of a actual component should be less than the shear yield strength in the uniaxial loading condition that we perform in UTM. Here you can see if there is a stress in this direction, force is applied in uniaxial direction, let us say in x direction, then there will be only a stress in x direction, that is only in one direction, so it is called uniaxial stress or uniaxial loading condition. Now how will our actual component, the complex loading condition will be somewhat like this. Here I have shown the stresses in x, y and in shear direction also, that is in the plane parallel to the, let us say, one edge. This is the one edge which is perpendicular to the x direction, and it is the shear stress in the plane which is perpendicular to the x direction. So as we are talking about the two-dimensional case, the in-plane stress or the maximum shear stress, if we will talk in plane maximum shear stress, it will be a tau max, and how we will represent it we will see in next slide. We can represent it as sigma 1 minus sigma 2 by 2, and in case of absolute condition, the absolute maximum shear stress will be the mod of maximum of sigma 1 minus sigma 2 by 2, comma sigma 2 minus sigma 3 by 2, and sigma 1 minus sigma 3 by 2. Whatever will be the maximum from these three condition or three shear stresses, that we will consider as a absolute maximum shear stress. So we will discuss only about 2D stresses. Just for your information, I will put sigma 3 equal to 0 because it is a two-dimensional case. So here this value becomes 0 and we will get this absolute stress, maximum shear stress. Now you know that in UTM at this plane, let us say perpendicular to x, there is no shear stress, that means shear stress is 0, so we can consider it as a principal stress. This plane we can consider as a principal stress because shear stress is 0, right? Now we will find the yield shear stress or shear yield stress, that will be sigma 1 minus sigma 2 by 2, and you know that in only one direction there is a stress, and in another direction, let us say perpendicular to x axis, it is 0. So what will be our tau max, that is shear yield stress or shear yield strength, it will be sigma y by 2. That is nothing but the 0.5 times of yield strength, or you can even write it like this, 0.5 times SYT. Sigma y is nothing but the yield strength, that is tensile yield strength in UTM if you are considering a uniaxial loading condition. Now, according to the statement of this theory, actual shear stress, maximum shear stress should be less than yield shear strength. Now we have find out the absolute maximum shear stress. It is like this, and it should be less than this value, that is 0.5 SYT or 0.5 sigma y or sigma y by 2. Now we will write the separate equations for this one and this one. We will equate each term with sigma y by 2, right? Now what will be the first equation? We will get from this sigma 1 minus sigma 2 by 2 should be less than equal to sigma y. The common terms we will cancel. The equation will be like this. So we will call it equation 1. Sigma 1 minus sigma 2 equal to positive sigma y, and we will call this equation as, say, equation number 2. We are writing this separately for drawing or plotting this equation on graph, because we want to find the safe region. Similarly, we will also write two equations for this equation. So we will write equation number 3, sigma 2 should be equal to, or sigma 2 equal to positive sigma y and sigma 2 equal to negative sigma y. Similarly, we will write equation number 5 and 6 from this. Here I have written it. Now we will plot this equation number 1. You can see from this equation sigma 1 minus sigma 2 equal to positive sigma y. If we are going to plot sigma 2 on y-axis and sigma 1 on x-axis, that means these are the variables. We are considering this sigma 1 and sigma 2 as variable. So let us say sigma 1 is x and sigma 2 is y. Then you know that x minus y is equal to some constant value. It is nothing but the equation of straight line. So these two are the equations of the straight line. So we will plot this straight line on the or coordinate system. Let put sigma 1 value equal to 0 for getting the points in this equation number 1. What we will get? We will get sigma 2 equal to minus sigma y. And let us say the equation from this, we are getting 0, minus sigma y. Right? This is point C. Let us say any point A. Now we will put sigma 2 equal to 0. Then we will get this point sig B. Okay. Now we will put these points on this graph. What our point A is 0, minus sigma y. 0 on x-axis, x coordinate is 0 and y coordinate is minus sigma y here. So we have got this point. Similarly, the second point is sigma y, 0. Y coordinate is 0. Now, if we will join these two lines, these 2 points, if we will join these 2 points, we will get a straight line having equation sigma 1 minus sigma 2 is equal to sigma y, which is similar to the equation of straight line. Similarly, we will put equations or lines for all these equation number 3, 4, 5 and 6, and we will get such a hexagon, which is an irregular hexagon because all the sides are not equal. And from this graph we can say that this is the safe region according to Tresca's theory or Guest's theory. Now we will discuss this equation or this safe region with a ductile material, and we will then finally compare it with the experimental result, whether this theory is suitable for ductile material or not. So What is our, just a minute, what is our statement of this theory? Actual maximum shear stress should be less than yield shear strength. So putting the values of shear strength, yield shear strength, you know that it is like this. It is 0. So sigma y by 2. Now this theory says actual maximum shear stress should be less than 0.5 times the yield strength, that is 0.5 times the tensile yield strength, right? And experimental result says that maximum shear stress should be less than 0.57 times the yield strength for ductile material. That means this theory is safe, and it is also known as a Overstep theory, and that's why it is mostly used and predominantly used for ductile material, design of ductile material components. As the name itself says that maximum shear stress theory, that means it is considering a shear stress. So it is, we can say that, suitable for the ductile material. So now we will discuss one example for this, which is the exceptional case. Let us consider these two conditions where the normal stresses, values of the normal stresses are equal. Both the normal stress, let us say sigma 1 and sigma 2, equal to 20 megapascal. Either it is in tensile nature or compressive nature. If it is a compressive nature, it is called a hydrostatic loading condition. From, you know that in all the direction there is equal stress or pressure on any component or smallest component of a material. Now by Tresca's theory, actual maximum shear stress should be less than the shear yield strength. So we will put these values. Sigma 1, you know that yield strength is calculated by sigma 1 minus sigma 2 by 2. Putting this value, and you are getting the maximum yield strength equal to 0. Right? Now, which is inaccurate result. Whether it can happen that a maximum shear stress equal to 0 even after applying load. That's why this theory is giving inaccurate results for hydrostatic loading condition. So for hydrostatic loading condition, we cannot use maximum shear stress theory. That's the drawback of this theory. Now we will go to the next theory, that is total strain energy theory or Haigh theory. What this Haigh theory tells, for safe design, look at the statement, for safe design, total strain energy per unit volume in actual compress loaded component or in compress loading condition of a component should be less than the total strain energy per unit volume in yielding, that means under uniaxial loading condition in simple tensile test. In short, here I can write it, strain energy per unit volume in actual loading condition should be less than strain energy per unit volume in yielding. You know that how total strain energy is calculated in 3D. It is like this: 1 by 2e sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 mu sigma 1 minus sigma 2 minus 2 mu sigma 2 sigma 3 and minus 2 mu sigma 1 sigma 3. Here you can take 2 mu common, but we are concerned with the 2D, so we will directly write the equation in 2D. The total strain energy per unit volume will be equal to 1 by 2E into sigma 1 square plus sigma 2 square minus 2 mu sigma 1 sigma 2. Mu is the Poisson's ratio, right? In uniaxial loading condition, the total strain energy per unit volume will be the half into stress into strain. We have calculated, or we got this value from the stress strain curve. You remember that, you may remember if this is our, let us say, stress strain curve, right? Then this much area, how we will calculate? You can see here, this is our stress strain curve. This is, let us say, point E. Now if you want to calculate this area, you will find it by using the formula for triangle, area of a triangle. You know that half into base into height. Here we are getting the half into sigma y, that in on this axis there will be stress and here will be strain. So half into sigma y into epsilon y is the strain energy. This sigma y you can write it like Sy t, half into Sy t into epsilon y. It will be in the joule per meter square, because this is the unit for stress, Newton per meter square, and meter per meter is the strain. Now, according to the statement of this theory, total shear energy, the total strain energy per unit volume should be less than total strain energy per unit volume in yielding, right? Y, this suffix y denotes the yielding condition, and this suffix a is the actual loading condition. We will put these values from the above formula. Half 2e into sigma 1 square plus sigma 2 square minus 2 mu sigma 1 sigma 2 should be less than sigma y square by 2e. We have got this from the stress strain curve. So final equation will be sigma 1 square plus sigma 2 square minus 2 mu sigma 1 sigma 2 should be less than sigma y square or Sy square, Syt square. After equating, you will get under root sigma 1 square plus sigma 2 square minus 2 mu sigma 1 sigma 2 should be less than equal to sigma y. I am not considering factor of safety here. If it is given in numerical or problem, you can write like this. From this, you will also get the FOS, how FOS is defined. That is actually the yield strength divided by the working stress. We will discuss about this in the last or in forthcoming lecture. Presently you forget this. So working stress we have got in Haigh theory, sigma 1 under root sigma 1 square plus sigma 2 square minus 2 mu sigma 1 sigma 2. Now from equation 1, that is this one, this equation, we will put or rearrange it. We will transfer the sigma y square to the left hand side. Here you can find we are getting a equation which is nothing but the equation of ellipse. So it is clear that after putting this equation on graph, we will get a ellipse shape. So let us find some points so that we can easily draw a graph, draw this equation on graph. Put sigma 1 equal to 0 in this equation. What we will get, these terms will become 0, this and 2. So sigma 2 square is equal to sigma y square, and sigma 2 will be equal to plus minus sigma 1. So we will find, let us say, point G and H on the graph and put it on the graph. Similarly, we will put sigma 2 equal to 0 in equation 1. So we will get sigma 1 equal to plus minus sigma 1. And that's why the equation will be, the points will be the point I, sigma y comma 0, and let us say point I, this point J will be minus sigma y comma 0. Now putting all these 4 points, and we'll draw a ellipse here. Here we have plot points G, H, I and J, right? I have got this shape. Now this maximum distance, or the maximum distance, or the axis which have a maximum distance, it is called a major axis, and it is given by 2 sigma y by under root 1 minus mu. This you can write as Fy also. And minor axis is equal to 2 sigma y upon 1 plus mu. Here you can easily remember that if we are subtracting mu from 1, and the value of this complete term will be lesser than 1, let us say. So if we are dividing any number or any value by a value lesser than 1, let us say 0.2, this complete value will increase, will be maximum. So this is the major axis of the ellipse, and if we will add any value to 1, so let us say it become 1.2, so the final value will decrease. That means minimum value we will get for this complete term, and that is nothing but the minor axis. Okay, by looking at this sign also you can remember. This can be asked in few exams like GATE and PSU. Now here you can see this region inside the ellipse is the safe region under this by this theory. Now checking whether this theory is suitable for ductile materials or not. So let pure shear loading condition, that is pure torsion. Here you can see this ductile material or machine component is under the torsion T. So if I will consider any point or smallest point in this and draw it here, it will look like this, which is in pure shear. So by drawing more circle for this condition, we will get the values for sigma 1 and sigma 2, that is sigma 1 equal to tau and sigma 2 equal to minus tau. Now we will put these values in equation 1. What we are getting, tau square plus minus tau square plus 2 mu tau square is less than equal to sigma y square. Finally we have got this value for tau. This, if you will put value of Poisson's ratio equal to 0.3, because for most of the materials value of Poisson's ratio is between 0.25 to 0.33. So finally we are getting tau should equal to 0.62 times the sigma y, right? And now we will compare this value of Haigh theory. this theory with the experimental result. According to experimental result, tau max should be less than 0.57 times the sigma 1. Here you can see there is a difference. Even at higher stress, the theory is saying that the machine component is safe, but experimentally, actually, it will be not safe. It will be safe until the stress value, that is 0.57 times, which is lesser than the 0.62 times the yield strength. So this is inaccurate theory. But if we will compare with the first theory and second theory, that is Rankine's theory and St. Venant's theory, it is a little bit closer to the experimental value. The value we are getting are closer to the experimental value. As compared to other two, Rankine theory and St. Venant's theory, it is a better one. But it is also not used for ductile materials because it is not giving accurate result or safe result. So this was all about the 4 theories which we have discussed, and in next lecture we will discuss the 5th theory. Till then, if you have any doubt, you can write in comment box. Till then, goodbye. Signing off for the day.